Yeah, in the next remaining part, approximately 1 hour, we'll talk more on the control part of the PV inverters. So first, if you look at the requirements of the PV system in terms of the, let's say, grid integration, then we have discussed a bit earlier that I don't have the pointer. Can you see my mouse in the slides at least?
Yes, we can see it. Yeah.
Okay. Now I have the pointer. Yes. So from the PV panels, then of course we want to achieve this maximum power point tracking. So all the time operate at the maximum power point, at least in most of the cases. And then also from the grid side, we have some requirement in terms of the power quality, right? So we have to make sure that, let's say, the current THD needs to be below a certain limit, for example. And also, in case of the large scale or some of the recent grid codes start to demand that you need to provide different control functionality as well to support the grid. And also from the PV inverters part, you need to, of course, have high efficiency, high reliability, and also, provide some other functionality like monitoring and also safety as well. So these are the general requirements of the control of the PV inverters. You can then look a little bit more inside, like what kind of control loops or different control blocks that we need to implement in the power electronics. So here we have some example of the two-stage PV system where you have a DC-DC converter and also DC-AC inverters. So of course, fundamentally in the end, how can you control this switch is based on your pulse width modulation signal, right? So you have some reference current, or no, sorry, reference voltage, and then you compare with the carrier to generate this controlling signal for your switch. But this reference should be generated based on different control loops. So if it's a DC-DC converter, then probably you have some current or some voltage control loops. If it's a DC-AC, you also need to have some synchronization, some current control, and also some DC link voltage control in this case. On top of these basic controls loops, you probably also need to have some what we call PV system specific controls, like maximum power point tracking. In many cases, you also demand to have some anti-islanding protection. And also lately, you also have to ask, to provide certain control functionality like power limit control. And that's we also discuss later on. Yeah, so you can classify into basic function of the grid tie inverters, and this also shares similarity with the, let's say, the wind turbine power converters. And there's also some other PV specific control functionality like maximum power point tracking, anti-islanding, and also some other part. And you can also take what we call ancillary service or ancillary support as an extra functionality that the PV system may need to provide for the grid support. We first look at what we call maximum power point tracking, which is one of the fundamental control method of the PV system. And we have seen earlier that for certain operating condition, there's a unique point which have the highest maximum power, right? And this is what we call maximum power point. And of course, in order to get the most PV energy out of the solar panels, then we all the time want to make sure that we operate at this point. So for example, we want to make sure that the PV voltage is according to this maximum power point instead of somewhere, let's say, higher or lower, because in that case, you end up with the power production lower than this maximum power point. The challenge is that, of course, in steady state, this curve is kind of constant. But when you have the change in the solar irradiance, or let's say you have more sun coming, then the curve characteristics start to change accordingly. And it means that the maximum power point will also move accordingly. Also depending on the solar irradiance, but also the temperature. So in general, when you have higher solar irradiance, which means you have more sun, you have a higher power production. So your maximum power point is increasing in terms of the power. But for the temperature, if you have high temperature, then usually what happens is that your current will not change so much, but your voltage will start to drop. So in that case, you can see that the area behind this maximum power point is also decreasing. So it means that you have a lower available power to extract. So for the PV panels, actually the best condition is to have high solar irradiance, so high sun, but low temperature. So that's when the efficiency of the PV panel is at the maximum, or let's say at the best. Now it's depending on different, or depending on how the structure of your system looks like. If it's a single stage, which means you only have a DC AC inverters connect directly from the PV panel to the grid, or if you have two-stage system where you have a DC-DC converter, it could be a boost converter, for example. And if you connect the boost converter to the PV panels, and then afterwards you connect the inverter at the DC link to the grid, then this is what we call two-stage system. Then you could have different implementation of the control structure. So we will go one by one. If you have a single stage system, so you have only one unit of PV of the inverters connect the PV and also the grid. In that case, the inverter needs to how to say, responsible for both maximum power point tracking, so you control the power extraction from the PV arrays, but also at the same time you also need to control the power injection to the grid. So you're doing both the DC side power control and also the AC side current, or can also say is a power control to the grid. One way to implement this is to have the maximum power point tracking algorithm. So you measure the current and then the voltage of the PV panels. So these are the DC components. And then you can, based on the algorithm, calculate what could be the output current based on this algorithm. Then you control the current directly. So in this case, you will need the maximum power point tracking algorithm, which can give you the reference AC current as the output. And this is not usually the case, actually. So in most cases, your maximum power point tracking algorithm will give you the voltage which have the maximum power. And in that case, you typically implement it in this figure where you have the reference voltage coming from this algorithm. And then you compare with the measure PV voltage. And basically, if it's a single stage, this voltage is also the DC link voltage, right? And you have DC link voltage controller to regulate this reference voltage. And by doing so, you actually generate the reference output current, and then you have the current control to do the regulation of the AC current. Or you could also add the power feed forward to the above control structure, because in many cases, you will not change from the previous operating point the voltage in the Y range. So you just change a little bit to see if you reach the maximum power point. So in order to speed up the dynamic of your control, you can also do power feed forward in this case. But of course, you have to be careful that in that case, you have also some noise propagate from this measurement directly feed into your reference current generation. But then you have a faster dynamic. So that's a trade-off. If you have two-stage system where you have a DC-DC converter on one side and then you have the inverter on the other side, then in this case, you normally implement the MPPT at the DC-DC converters. So one way is that you have the algorithm to generate what is the duty cycle of the DC-DC converter, which has to be regulated to basically keep the operating point of the PV arrays at the maximum power point. Then the power will be actually extracted from the DC-DC converters. So the inverter then just need to regulate the DC link to be constant. because if you can regulate the DC link to be constant, then you can make sure that the power extract from the DC-DC converter will be injected to the grid, and there will be no extra power keep in the DC link. You can also add the feed-forward term in a similar way as the single stage over here, and of course the same trade-off also apply, that you have a faster dynamic, but you have also more sensitive to the noise. So these are the different structure that you can implement maximum power point tracking. Now in the next couple of slides, we will look more into these blocks, how we can actually implement, or what are the algorithm behind the maximum power point tracking. One of the most commonly used method, and also today is one of the very, how to say, popular in the commercial product, is what we call perturb and observe, or sometimes we call it the P&O, maximum power point tracking. And the idea is very simple. So if you look at this, the power voltage curve, the red curve here, you can see that, well, depending on where you are in this curve, if I change the operating point intentionally, and then I observe the change in the power, I can actually figure out if I'm going far away from the maximum power point, or if I'm moving toward the maximum power point. So let's say we start from this operating point. Now, if I increase the voltage, then it means that I will probably end up somewhere here, right? And I can say that by doing so, the output voltage, the output power will decrease if I move from here to here. So in that case, I know that, oh, actually I'm in the wrong direction. I should go in the opposite way. So it means that then the next sampling, then I should move back here and then move in the same direction, go forward. So when I move from the right to the left over here, then I can see that now the power is increasing. So I'm moving in the right direction, right? So I should keep going forward in the same direction. So that's why we call it a perturb and observe. So we perturb the operating point. It could be either increase or decrease the voltage, and then we try to observe what is the change in the power. So if the change in the power is in the positive direction, it means that you're on the right direction. So you keep going in the same way. But if the change in the power is in the negative value, it means that actually you're moving away from the maximum power point. So you should reverse your perturbation direction. And that's what you can also see from this flow chart. So first you check if there are any change in the power, because ideally when you're at the top of this maximum power point, your slope will be 0, right? So there will be no change in the power. Of course, in practice, you always have a small change in the power. So in practice, you never really end up in this as a yes, but usually you end up here as a no. And then you check if the power has been increasing from the last perturbation. Then if you say, yes, the power has been increasing, then you check if the voltage has been increasing. So if the power is increased and your voltage also increased, it means that, well, you're in the right direction. Just keep increasing the voltage. But if your power is increased over here, and then your voltage is decreasing, then you go into this logic where you say, okay, then you should keep decreasing your voltage, and you just do the opposite direction over here. So if your power is decreasing, and if your voltage is has been increased, then you should decrease, and the other way around. If you have been decreased the voltage, right? So that's the basic idea of this method, and it's actually very simple to implement. Just a few if else. The advantage is that it's very simple, and also, yeah, like what I mentioned, it's very low computational demand, so it's very easy to be implemented, and it doesn't take a lot of resource in your computation. It also has some benefit in terms of the generic. It means that you don't actually need to know how the characteristic of your PV array looks like. You can always apply this to any PV arrays. So that's the good thing, that you can apply to basically any system. The disadvantage is that there's a trade-off between the speed and the accuracy. And the main reason is because it's kind of a iterative algorithm, right? So you have to perturb and observe and then perturb again and again. So if you are somewhere very far from the maximum power point, it could take a few samples until you actually reach the maximum power point. So that's the trade-off between the speed and accuracy. And another disadvantage is that it's also sensitive to the change in the environmental conditions. So it can get confused when you have some change in the power. And that's, I will try to demonstrate here in these figures. From the left top figure, you can see that the green plot is the change in the solar irradiance. So we apply kind of a trapezoidal solar irradiance. So you have some steady state over here, and then you have some dynamic condition. You have steady state again, and then you have some decreasing irradiance. And the red one is actually the ideal voltage. So this is the voltage at the maximum power point of the PV array. So it's the real maximum power point voltage. The blue one is the voltage of the PV arrays, which is based on this perturb and observe method. So you can see that in steady state, you have a little bit of oscillation, and that's because when you are actually at the top of the hill, so to say, then you perturb, let's say, if you come from the right direction, then you perturb it to the left, and then you will start to see that, oh, now the power is decreasing because you fall off the hill. So you will reverse the direction, and then again, you will go back and forth because, yeah, when you go 2 steps on the right, then you again go down the hill. Then you go back maybe 2 steps, then you go down the hill again. So you keep oscillating around the maximum power point in the steady state. And that's the characteristic of this algorithm. And that's what you see over here, but also over here in the steady state. Now, when you have to start to have the change in the irradiance, what could happen is that, of course, you change the voltage and then you try to measure the change in the power. And you assume that the change in the power comes from the change in your PV voltage, right? But if your solar irradiance is changing, it means that the change in the PV power could come from both the change in the operating point of your voltage, but could also be because just that they have more sun, so you have more power. So what happened in this case is that actually the perturbation go in the wrong direction, right? So it's decrease the voltage instead of increase, which should be in if you want to follow the real maximum power point in the red line. So even though you go in the wrong direction, but because the irradiance is increasing, so you still see the positive change in the power, at least until this point. And because of that, then you can see that the algorithms keep going in the wrong way because you still see the positive change in the power, even though it's not the ideal direction. Until this point, when the algorithms start to catch up with the change in the power, then you realize that, oh, I'm in the wrong direction. Then I have to go in the opposite way, and they start to go back to the real maximum power point. And you can see that it takes quite a lot of sample until you can reach the maximum power point, and then you have some oscillation in the steady state. In the lower figure, it's actually exactly the same algorithm, but in this case, in the first step, when you have the change in the irradiance, instead of decreasing, it increased the voltage as a first step. And then the same thing happened is that because of the change in the irradiance, it keeps going in the same direction until certain point. In this case, it's a bit better because you are closer to the real maximum power point. So if you look at the power extraction from this two case, you can see that compared to the ideal power, which is the red curve, you have some loss in the energy extraction over here during the increased irradiance. And depending on if you start from decrease or start from increasing in the perturbation, you end up in a little bit different in the energy loss. But in both cases, these are the drawback that you have some energy you lost because of the confusion in the tracking when you have increase or when you have the change in the solar irradiance. Another popular algorithm is what we call incremental conductance. And instead of looking at the change in the PV power, what this algorithm is doing is actually monitoring the the slope of the PV curve. So basically, we know that at the maximum power point, you have the slope is actually 0, right? If you look at the PV, delta P over delta V, why on the right side, your slope will be negative, and on the left side, your slope will be positive. So if you check the slope all the time, you can actually figure out if you are at the maximum power point, or if you're on the right side of the maximum power point, or if you're on the left side. So basically, from differential equation from delta P over delta V, you can actually derive into this different equation from the current and then the voltage. So you have the PV voltage multiplied by delta I over delta V, and then plus I. And this delta I over delta V is actually the increment. It is a conductance, right? So it's I over V. And that's why they call this term as incremental conductance. So basically, you monitoring this term, V delta I by delta V plus plus I. And basically, if this term is 0, then you're at the maximum power point. If this term is positive, then you know that you're on the left side, and it means that you should increase the voltage to go to the maximum power point. If this term becomes negative, it means that you are actually here on the right side, so you should decrease the voltage in order to go to the maximum power point. And that's exactly what this flow chart is telling you. So first you do some perturbation, so that means that your the delta V will not be 0, so you go to this condition, and then they check, okay, if this term is 0, it means that you are at the top of the maximum power point. If yes, then you do nothing. And in the next step, then if you didn't perturb or if you didn't change the voltage, it means that you will go to this loop. And then if the delta V is 0 and also there's no change in the current, it means that you're actually at the maximum power point and there's no change in the solar irradiance. So you should do nothing. But of course, in real life, this condition doesn't really apply for the same reason as the perturb and observe method. So you always have a small change in the slope. You never really get this 0 slope in practice. So if you have if the slope is not 0, then you just check if it's a positive. Yes, it means that you are then on the left side, right? Then you have to increase the voltage reference. If the slope is negative, then you're on the right side, and then you have to decrease the reference voltage, and then you keep going in the next perturbation. So some people say that this method is better than perturb and observe because you're kind of monitoring if you're on the left or on the right side of the slope. But in practice, it's have quite similar performance because in practice, when you have the change in the solar irradiance or even the temperature, then you cannot rely anymore on this slope because just your change in the slopes can also come from the change in the power. So in principle, they have almost the same performance, the perturb and observe and the incremental conductance. And because of that, sometimes people just call these two together as a hill climbing method. So basically what the algorithm try to do is to climb the hill. So it's try to kind of perturb or change the operating point in a way that you reach the top of the hill with under a certain number of iterations. Another method that you could also apply is what we call constant voltage method. And in this case, it's kind of an approximation, because if you look at the characteristic of the PV modules, you can see here is the current and the voltage under different solar irradiance condition. You see that especially at the high irradiance condition, the voltage of the PV at the maximum power point is almost constant. And actually, if you compare this with the open circuit voltage, the ratio between the maximum power point voltage and the open circuit voltage is approximately constant, or is very close to constant in a wide range. So sometimes people just said, okay, then I can approximate that if I know the open circuit voltage, then I can apply directly the reference voltage. How to say? Normally, the maximum power point voltage over the open circuit voltage is approximately allowed around 76%, 78%, depending on the type of the cell, and it doesn't change quite a lot. So in many cases, if you measure the open circuit voltage, then you can directly apply the reference voltage, which is around 76 or 78% of the open circuit voltage as a reference, and then you will be very close to the maximum power point. The good thing is that, well, in this case, you don't need to do any perturbation, so you can go in one step to the maximum power point or to somewhere close to maximum power point. But in order to do that, you need to know the open circuit voltage. And normally you can do by you disconnect the load, then you measure the open circuit voltage, then you set up the reference according to the fraction between this maximum power point and then the open circuit voltage. And then you do this again, I don't know, maybe every 5 minutes or 10 minutes, depending on how often you want to do this tracking. So the advantage is that it's very simple and there's no steady state oscillation like the other method. The drawback is that you have to measure the open circuit voltage. And when you do that, you basically don't generate any PV power because you have to go to the open circuit voltage where the power is 0. Another drawback is that the ratio is, of course, approximation, and it's not all the time this 76% or 78%. It also changes with the cell technology, but also the temperature also have a big effect on this as well. And not to mention that when you have the certain aging, the characteristic of the PV cell also change. And in that case, you cannot really rely on this approximation anymore. So it's not very accurate, but it's very simple and fast. So that's the trade-off between advantage and disadvantage of this method. So some people say, well, then why don't we combine different methods to get the most out of it? Because one of the drawbacks of this hill climbing or perturb and observe and incremental conductance is that when you have quite low irradiance, you can see that the curve, the power and the voltage curve is quite flat. So it means that when you change or you perturb the voltage, you don't see a lot of change in the power. So it's very sensitive to noise. So if you have a lot of noise, then you can easily get confused because what you're measuring is maybe be confused by the noise. And in that case, in many times it's more convenient to use the constant voltage method when you have the low irradiance. So try to avoid getting confused with this flat curve. But when you are at the high irradiance, then you can use the hill climbing method or the perturb and observe. So that's what you have over here as a combination. You can see that first you check the PV current if it's higher than 0.7, and this is of course for specific PV panels. If it's higher than the certain range, then you do perturb and observe, and that's what you have over here. But if it's lower than this limit, then you can do the open circuit or this constant voltage method. So it's kind of a combination, and then by doing so you try to improve the efficiency during the low voltage, but at the same time try to get the most during the high irradiance condition. So this slide just to kind of summarize the characteristic of different maximum power point tracking approach. So this the hill climbing method, which is based on perturb and observe or incremental conductance. The advantage is that it's very simple and also have a low computation burden. It's also quite generic, which means that you can apply to any solar cell or PV technology without even know the characteristic. But of course, it's a kind of a iteration approach. So it means that there's a trade-off between speed and also the accuracy. And later on, we will talk a little bit about how to design the parameter of this maximum power point tracking, considering this speed and accuracy trade-off. And we have shown earlier that it could get confused when you have some change in the solar irradiance because of this measurement in the change in the power. It is not all the time coming from the perturbation, but it could come from just that you have more sun now. If you compare this with the constant voltage method, then of course this is one of the most the simplest method is a constant voltage. You just need to measure the open circuit voltage once in a while, and there's no ripple due to the perturbation. But the disadvantage is, of course, that it's not very accurate because it's kind of an approximation, and you have to sacrifice some energy U because of this open circuit measurement. Yeah, you can also, instead of check the open circuit voltage, you can also check the short circuit current, and it's kind of the same approach that is almost constant over the wide range. And there's also other maximum power point tracking, which we don't have enough time to cover here. But the key message is that the perturb and observe is still one of the most commonly used maximum power point tracking today. And this is how it looks like when you really implement in the real system. So we try with the one-day operation where you have a cloudy situation, and you can see that the available power is changing up and down all the time over here. And another case, you have a quite smooth, clear day condition. And the red plot is the available power you can actually extract from the PV. And the black one is the extract power from the maximum power point tracking based on the perturb and observe method. So in general, you can see that it still works quite fine during most of the case. So, and that's also the reason why the perturb and observe is still widely used. Of course, you have a little bit of some loss of energy, let's say over here, for example. And if you zoom in, maybe doing the fast chain, you will not ideally track the maximum power point. But in general, it's still quite good enough in many applications. Another issue for the maximum power point tracking, especially for this hill climbing method, is that if you start to have some shadow over some part of your PV power plant. So for example, you have a lot of PV modules connect together, and some of them start to have some shading or some shadow. What happens is that instead of having this ideal power voltage characteristic with the single peak power, you start to have a multiple peak depending on how much shadow has been covered. So on the left figure, you can see that if you have different level of shading, so if 1/4 of your panel is shading and the shade increase, if the shade increased, then you can see that the one that got shaded, we have much lower power. And what happened is that in the end, you will have this multiple peak characteristic depending on how much the shade has been on. But also, if you have the same amount of shade in terms of like how the same shadow, but the area is increasing, you also have the same issue where you end up with a multiple peak. And the problem is that depending on where you are in your MPPT algorithm, you could end up tracking this local peak instead of the global peak. Because if you, let's say, start from the open circuit voltage and then you keep tracking based on the perturb and observe, then you will probably stuck in this local peak because the algorithm actually doesn't know that after this there's another peak. So when you reach this peak, you already think that, well, this is the maximum power, and it's keep oscillating around this peak. And this means that you have a big loss in the energy U, right, compared to the global maximum power point. And this is some example where we applied a long-term 50 minutes operation, and we start to introduce some shading during the operation. So if you look in the time series over here, the green plot is the global maximum power point. So it's the, let's say, the ideal condition, while the red one is what the maximum power point tracking is actually doing. So you can see that when you don't have shading or you just have small shading, then the maximum power point tracking is it's kind of okay in terms of tracking the global maximum power point. But then at some point, it starts to diverge to this local point. And then after some time, this go back to the maximum power point. So these are basically the energy loss for you if you use this conventional method, and then you have multiple peak, and that could be an issue. What you can do, and that's maybe one of the simplest method, but of course you have to sacrifice with some energy use, is that you can sweep this curve. So what we normally do, at least, or what the industry do, is that you sweep the operating point from open circuit voltage to short circuit. So basically you try to draw this curve, or to find out where is the global peak, and then you directly apply this operating point as a reference, because after sweeping, then you actually know where is the global peak. The good thing is that then, well, you kind of make sure that you are all the time at the global maximum power point instead of the local maximum power point. The drawback is that then, of course, it's a bit like when you measure the open circuit voltage, right? So you have to interrupt the operation and then sweep this operating point, so you lose some energy use during that period. But it's maybe one of the most robust method compared to different shading condition and also different panels characteristic. We can also talk a little bit about how should we design the maximum power point tracking algorithm. And this is one of the very important, I would say, issue for the PV MPPT design, because when we look at this hill climbing method like perturb and observe, or even the incremental conductance, one of the performance parameters that you need to decide is what is the step size of your perturbation. So how big is your step should be. If it should be like 5 volts, you change in the reference, or should it be 20 volts or even bigger? And also how often should we do the perturbation? So ideally, if you do the perturbation very often, it means that you can actually catch up when you have the change in the irradiance quite fast. So you will be faster. Or if you have a larger step size, it also means that you will follow the change in the irradiance much faster. So for the same range of the voltage, if you apply high step size, you take less iteration, right, to reach the maximum power point. So usually they recommend to look at the change in the voltage over time. So this is kind of the definition of the speed. So it's a volt per second, not just the step or just the sampling rate, but the ratio between the step and also the sampling rate. And this reference have quite some good intensive study where you try to apply different operating condition and try to measure what is the impact of different tracking parameters in terms of the efficiency. And what they found now is that if your tracking speed is too low, which is end up over here, then of course you have a low efficiency. If you start to increase in a certain range, then you will see some improvement. And at some point, if your tracking speed is fast enough, it doesn't make any improvement if you make it even faster. So they recommend us around 0.1 to 1 volt per second. Oh, sorry, percent of the maximum power point voltage per second is kind of the recommendation. Because in this case, you kind of make sure that your tracking efficiency is very close to 100%, and that's what you want from the maximum power point tracking. Because in this case, it's just a software efficiency. So in principle, it should be as close to 100% as possible. Yeah, we talk about this step size and also the sampling rate, because these are the two parameters that actually affect the performance of your tracking algorithms. So the perturbation frequency or the sampling rate of your MPPT, first it has to be limited by the converter dynamics, because when you change the reference voltage, your converter also, depending on the switching frequency and also the hardware design, it takes some time until the PV voltage reach the steady state, right? And you should not apply the next perturbation before the voltage reach the steady state. Otherwise, you will get some errors. So on the high side, you are limited by the converter dynamics. But on the lower side, if you sampling too slow, then of course you cannot follow the change in the environmental condition. If you look at the perturbation amplitude or the step size, again, if you use too small step size, then you cannot follow the change in the environmental condition, but also you are sensitive to the noise if you have some ripple, for example, in the voltage or the current. If you use too large sampling rate, then in the steady state, you have also the large oscillation, because if you remember, we are oscillate around the maximum power point. So if the step size is large, of course, the oscillation also will be large. Yeah, and these are some of the concern that you can apply when you decide the maximum power point tracking. The way to verify if your design parameter is good enough is basically just to test with the standard testing profile. And you have a EN, this 50530. It's kind of the standard profile that you can use to test your MPPT algorithm. And basically, it's just a repetition of this trapezoidal with different slopes. And this is maybe very important that when you want to test the maximum power point tracking, you should not try to test with the step response, because it's not a PI control, right? So it's kind of an iteration. So actually, test it with the step response doesn't make any sense, because if you use the large enough step size, you can always be very close to the final value with the one step. But actually, that doesn't tell the whole story, because in steady state, you will have some problem. So from the standard, you should always test it with a repetition of the trapezoidal. And you can find it also in this reference. It's important to also test with the different speed of this slope, because as you can see over here, depending on the steepness or the changing speed of this trapezoidal, you could have different efficiency. And what you can see on the left side is the first version of the MPPT algorithm that has been implemented over here in this specific inverters. And they have two conditions. One is when you change the minimum from 10 to 50%, like what you have over here. And the red one is when you change from 30 to 100%. So this is for the wider range condition. And you can see that the efficiency is not very good for this specific design. So in some cases, the efficiency is around below 90%. So this is quite bad, actually. But when you know this could be the problem, then you can actually update or change the parameter, or they call it a new format, and basically just change the parameters. Then now you go back to quite high efficiency. So it's around close to 100%. So in this way, you can test your algorithm and then improve it before you actually deploy the product. Yeah, so we have talked so far about this maximum power point tracking, and that's also quite a big issue with the PV system. So there's different algorithm, and also there's different concern in terms of the implementation. We haven't talked so much about the inverter part, and the reason is actually because it shares quite a similar structure as the wind turbine or even motor drive in some case. And for the single phase, the inverter control part, you can either control in a DQ frame, and over here you have the outer loop, which regulates the DC link controller. You have also, if you want to inject the reactive power, you also have a possibility over here with the Q-axis current. Then you have current control in the DQ frame, and this will give the reference voltage of your inverters. You can also do in the alpha beta frame if it's a single phase. So in a very similar way. If it's a three phase, then of course you can do also in the DQ frame like similar to what we have in the slides before, or alpha beta, and even in ABC frame, but maybe this is something not very popular nowadays. So in many cases, we tend to use the DQ or alpha beta frame control for the inverter part. Yeah, just a little bit about some functionality of the PV inverter in terms of the harmonic compensation, because in the end, when you want to connect to the grid, you have to follow the grid code. And one of the requirements is that, for example, your THD has to be below 5%. And for the PV system, there's of course there's some background harmonics, or there's some dead time issue that could actually affect your power quality. But also with the grid connect structure, you also have a potential to improve the harmonic with the harmonic compensator. So if you look at the typical control, current control, if you do the DQ control, then maybe you use the PI controller, right? Or if you do the alpha beta, then you have the proportional resonant controller, which have a resonant frequency at your fundamental. And then you can actually add on top of that the harmonic compensator, and this could be based on, for example, the multi-resonant controller. So you have certain harmonics you want to target, or you can also add some repetitive controller, which is kind of a multiple resonant controller. So this is just to give you an idea that in some case, if you have some harmonics issue, you have also possibility to compensate it with your current control. And this is just some example. When you don't have the harmonic compensator, then your THD could be a little bit above the limit. But then you can add the harmonic compensator to improve the power quality, and then you are below 5%, for example. Yes, so those are the basic control of the PV inverters, which you need to have. And what I'm going to present in the next few slides is about, we can also do some advanced control of the PV system. And in many cases, this start to become a demand from the grid. And the reason is because, well, you have seen in some of the previous slides that depending on the environmental condition, the power inject from the PV to the grid can fluctuate quite significantly, right? If you have a lot of cloud passing. So this could cause some issue, because all the time you want to balance the generation and then the demand. And this may be not very easy if you have a lot of fluctuation power coming from the PV panels. There has been some issue like overloading during the peak power generation, and also you have some voltage fluctuation when you have some passing cloud, and maybe even some frequency variation. So to solve this problem, then instead of doing the maximum power point tracking all the time, like what we have discussed earlier, then the grid start to require that maybe you need to also be a little bit more flexible. So that's what we call the flexible active power control. This is one of the examples that the Danish grid codes start to demand for the PV system, especially in the larger scale. So instead of all the time track the maximum power point, like what you have over here, there's some period maybe you have to provide a certain amount of the power reserve, because if you provide a certain amount of the power reserve and then you have the under frequency situation, then you can actually provide this to support the grid to increase the frequency and then balance the power generation and then the demand. You could also probably be asked to limit the changing rate in your PV power, follow a certain ramp rate, because you don't probably, the grid doesn't want you to inject too much fluctuation power to the grid. So there's some constraint you need to follow. And also during the peak power generation, in many cases you will be asked to limit the power to a certain point to avoid the overloading. So you have to kind of curtail certain power above this limit. So these are the three functionality that start to become more and more relevant also for the PV system. So if you look at the first control strategy, which is a power limiting control, and the idea here is that you have a certain limit where if the available power is below this limit, then you're allowed to operate with the maximum power point tracking control, like what we discussed before. But when the available power is start to be higher than this power limit, then you have to keep the power constant at this limit instead of tracking the maximum power point. So that's the idea. And if you again look back to this power and voltage characteristic curve of the PV arrays, then when you have the low irradiance level and then the power is still below this power limit, then you can actually follow the maximum power point tracking. That's fine. But when your power starts to be higher than the power limit, so if you go from the blue curve to the black one, then instead of following the maximum power point, you need to keep the power to be constant along this line, right? And you can do that by keep decreasing or actually you can also increasing the voltage along this line and keep the power to be constant. So instead of tracking the maximum power point, you have to follow this maximum power limit instead. This is how it looks like when you implement in the real system during 1 day operation. So of course, in this case, it's a little bit extreme just to demonstrate that you can actually go down to 50% of your peak power if you want to. And then in this case, instead of tracking the maximum power during this period, then you keep the power to be constant during both clear day and also the cloudy day condition. You can also be asked to limit the changing power to a certain rate. And this is what we call the ramp power control strategy. So it means that if your changing power slope start to be higher than a certain limit, then you have to follow this ramp constraint. And the way to do it is that you actually monitoring the changing rate in your power. So you basically monitoring the changing rate over time. If your changing rate is still below the certain limit, then you're allowed to operate with the maximum power point. But if your changing rate start to increase and then it's reach or even higher than the certain limit, then you have to reduce the power in order to make sure that your delta P over delta T is within the limit. So you then move away from the maximum power point. And the way to implement is actually a similar concept as the power limiting control. So if you provide this functionality, then you can see that the output power is regulated to a certain RAM constraint instead of following the maximum power. And you can also see from the slope that we measure over here that is kind of most of the time below this limit. Yeah, you may be also asked to provide a certain power reserve to the system. And in that case, this amount of the power that you provide as a reserve can be supplied later on when the grid is need. The idea here is that instead of tracking the maximum power point, you need to operate to a certain level below this available power with a certain amount of the power reserve. And this is what we call the delta P. So you're like operating a bit like a shadow compared to the maximum available power. And in this case, of course, you need to know what is the available power. If you know that, you can actually then limit the output power according to the available power, subtract by a certain amount of the power reserve. So it's a little bit similar to the power limiting control, but you need to know the available power to calculate the power limit level, basically. So if the red line here show the available power, you can actually inject to the grid. The black one here is show the power extraction that you need to follow in order to all the time provide a constant amount of the power reserve, delta P over here. So it means that when you're when the power is, when your extract power is below this limit, then you can operate with the maximum power point tracking. But when it's above this limit, then you have to keep the power to be at this level by reducing the output power. And this is how it looks like when you provide certain amount of the power reserve. So you can see that when we activate this power reserve control, then the output power of the PV is kept below the available power with a certain delta P, which is 200 watt in this case. And it means that during this period, you have 200 watt that you can provide to the grid. So you can increase your power with a certain amount of 200 watts. if it is need. Yes, and I think that's cover pretty much the control of the PV system, since from both the PV panel size. We also talk about the topology of the PV inverters and also some control that specific to the PV system, like maximum power point tracking, how to test, and also how to design the parameters. We also talk a bit about the general control structure, and in the last part, I think we give a little bit idea about what could be the advanced control that in the future it become more relevant to the PV system. And also make a list over here to give some good reference where you can check about further reading, covering, I think, all of the aspects that I've been discussed today. I'd also like to give some acknowledgement to many people who helped me preparing this material. And yeah, thank you very much for your attention.